All right, in this video, let's look at a couple applications of Kepler's third law. So number one here, a comet is in a circular orbit around our sun. If the comet is 8.7 AU, or astronomical units, from the sun, what is the period of the comet's orbit in years? So one thing that's nice about our solar system and the Earth, for example, is that the period of the Earth in years is 1 year, the time it takes to go around the sun in one full orbit. We also know that the radius of the Earth, now this is the orbital radius of the Earth around the sun, is, or the distance, the radial distance of the orbit as it goes around the sun, is what we define as 1 astronomical unit. So 1 astronomical unit is the approximate distance from the center of the sun to the center of the Earth, or the Earth's orbital radius. So when we look at any other planet in our solar system, if we have, or a comet, any other object in orbit around the sun, and we know the radius of that comet is 8.7 astronomical units, and we want to find the period, Kepler's law becomes very simple. Right? We know that the radius, orbital radius of the Earth cubed over the period of the Earth squared is going to equal the orbital radius of the comet cubed over the period of the comet squared. But if the orbital radius of the Earth in astronomical units is 1 and in years is 1, then this whole side just becomes 1. Now notice, because this is a ratio, as long as I'm consistent, as long as I have years and years, or seconds and seconds, or minutes and minutes, hours and hours, astronomical units, meters, meters, kilometers, kilometers, you can use any unit with Kepler's third law because it's a ratio, so you don't always have to convert. But just be wary of what unit you're in. All right, so this case, multiply by t squared, and then square root both sides. So I get the period of the comet will be the square root of 8.7 astronomical units cubed, and that gives me a period of 25.7 years. Okay? So there's example number 1. Now in example 2, we have planet X located at a certain distance from its sun. We don't know which one. And their revolution time in years, 2.4 years. Then we have planet Y, same sun, so that's a key because then that mass becomes constant and cancels out. Period of 8.6 years. How far is planet Y from its sun? So similar approach, except this time, instead of having the period be 1 and the orbital radius be 1, as is with our Earth, we're going to have to account for both. So we have the orbital radius of X, which is 4.5 AUs, the period of X, which is 2.4 years, and then we have the period of planet Y, which is 8.6 years. We want to know the orbital radius of Y. So again, we can set up Kepler's third law. Rx cubed over tx squared is equal to ry cubed over ty squared. Since we're solving for ry, I'm going to multiply by ty squared. And so we get ry cubed is equal to rx cubed times the ratio of ty squared to tx squared. That's one way you can write it. In this case, we have, I guess if we want to cube root it now, we get ry is equal to rx times the cube root of ty squared over tx squared. And this is, what do we got, 4.5. And the cube root of 8.6 years squared over 2.4 years squared. which gives me an orbital radius of 10.5 astronomical units. So there you have it, solving problems using Kepler's third law. One thing to note, make sure you're paying close attention to units. So whatever units your orbital radius is in has to be consistent. Whatever units your period is in has to be consistent.